things to look at. You can pass them around if you like, but I'll maybe do them later. No, I have a picture of one. I have a picture of one. If you've got one of the original ones, yeah.
I've actually got one in my pocket.
Can I pass it round?
Yeah.
Okay. Well, good afternoon, gentlemen. I've given this a slightly amusing title because I'll very quickly tell you where the expression Bodger comes from. Many years ago, Bernie and I worked at Pi Telecom many years ago, and I worked with a guy who was a RF engineer, and he was an absolute everything by the book. And his two bosses and the two senior engineers were the sort of people who would sit there with a bag of capacitors until it worked and then send it out of the door. And he used to rant on about bodgers. So that's why I've called it that. I've not been a professional RF engineer for nearly 30 years, so I like to consider myself as a bit of a hacker. So this is not a detailed thing. I just want to try and let you see what I've been doing with some LDMOS amplifiers and a little bit about my hacker's approach to making amplifiers that weren't designed for 23 SEMs work on 23 SEMs. So I've called it How to Get Serious SHF Power Without Really Knowing What You're Doing. Well, first of all, LDMOS stands for Laterally Diffused Metal Oxide Semiconductor. It's basically a power FET, but it's a power FET that's designed for RF work. And it has some very nice features. The main nice feature it's got is, unlike ordinary transistors, the source is right at the bottom on the base of the structure. And as you know, with RF amplifiers, generally you want to ground the source as well as possible. So you can actually bolt the whole thing down beautifully thermally and electrically to ground. So you've no nasty beryllium oxide in there to kill you when you so open it up. And it's very nicely laid out as a device. You can put matching circuitry inside it. You can internally match the device, and a lot of the higher frequency devices are actually 50 ohms in and out. So what I'm going to talk about now isn't actually needed. Typically, you can get LDMOS that operates up to 4 gigs. It's probably more than that now. They're relatively high voltage things. They're 28 or 50 volts. They do work at 12. Bernie's done one with a 28 volt device at 12, and you just get less power. And you can typically get 100 watts at 2 gigs from a device like that. And they're ever so easy to make. They have a positive gate bias. You can disconnect the gate bias, it doesn't blow up. And many years ago, when I did design RF amplifiers, I used to have a box next to my bench with dead transistors in it. Because the old bipolar devices you used to destroy them on a regular basis. But these, I've built 7 or 8 amplifiers of my own design, plus I've messed around with these. And I've only ever managed to destroy one. And messing around with them has involved putting the whole thing on my wife's hot plate to heat the thing up to desolder them. So I've tried quite hard. So that's a little bit about what LDMOS is. It appears in a lot of 900 meg amplifiers. If you're an amateur and you want some power on 23 SEMs, you've got a few choices. You can get your checkbook out and send your ill-gotten gains over to Germany, and you can buy one from DB6NT. They're beautiful. They're really lovely. They're lovely made. They work. They produce all they do. But they are a little expensive if you're unemployed like me. So that's one choice. You can buy one. You can grow your own. You can buy the devices. You can get a slab of copper. You can make a printed circuit board, and you can make one. I've done that. This is the plug. Hopefully, in the next either June or July Radcom, there'll be a design for a 23 SEM PA, and I will be doing bits. So you can grow your own, and there's kits available from. There's a guy in Germany who does them. There's a few other places you can buy kits, and you can just assemble it, and it works. Or you can get something surplus and modify it. And Chris has very kindly handed me this. if you can hand this round. This is a 900 meg amplifier. It's part of a bigger amplifier. Each one of those amplifiers will produce around about 100 watts, and there's 4 in this box. So you have the potential for 400 watts on 23 SEMs. But unfortunately, they're on 900 megs. And if you plug them in, if you plug them in and try and make them work on 23, they don't. So you've got to do something about this. You've got to remake them. You've got to redesign them. Chris is going to tell you later on what he's done with them, and I'm going to tell you what I've done. His is very professional. Mine's a wonderful bodge. So it's all about impedances. If you change frequency with these devices, their impedances change. So you try and put the wrong frequency up and they don't work. They're very low impedance devices, typically less than 1 ohms or around 1 ohms, resistive and reactive. So they look like a very low resistance in series with an inductor. So what you've got to do is you have to match them to 50 ohms over the bandwidth you want to match. And in very simple forms, that is the block diagram of a power amplifier. You've got a device in the middle with its ground, as I said, connected by this lovely fact that the source is on the bottom. You need to put gate bias on it, you need to put drain bias on it, and you need to match the input and output impedance to your system impedance, which is normally 50 ohms. So what you have to do is, if you've got an amplifier that's working on the wrong frequency, you first of all got to work out what the guy's done at 900 megs, and you have to stretch that somehow and move it to a different band. But there's a thing that you need to be careful, and I'll talk a little bit more about this. I mentioned internal matching earlier on. When you get to the really high power devices, they have the matching circuits on the chip, and if you try to externally match them, they just don't work. So you have to know a little bit about the device. But basically, this is your problem. That bit can stay the same, whether it's 900 megs or 1200, but you have to alter this and you have to alter this, or else it just doesn't work. So it's the impedance is stupid, to paraphrase Mr. Clinton. So the Bodger's design process, rather than the professional's design process, you've got to make the device look like 50 ohms in and out by transforming its impedances over the required bandwidth. And you've also got to make sure that by doing that you don't make it go unstable. So this is what you're going to have to work on and see what you can change. And once you've actually decided what to do, you've then got to implement it. And it might involve changing component values. It might involve taking a scalpel to the tracks and changing the size of the tracks. Various things that you can do. So you have to find what to change. So we get a device data sheet, right? Easy. Look at the data sheet, see what the impedances are at 1200 megs instead of 900, and you're laughing. No, you're not. Unfortunately, very rarely do you get manufacturers' data sheets outside the normal mobile phone bands. So they'll give you the data between 900 megs and 930 megs. If it's a higher frequency device, they'll give you the data in 2.1 gigs or 1.9 gigs. So you've absolutely no idea what the impedances do, because they are going to change. And the reason they're going to change is you've got a physical structure. It's resonant. That's what determines the impedances. So you change the frequency, the resonant frequencies change. So what on earth do? You haven't got the right data sheet. Believe me, I've tried assuming the impedances are the same at 900 megs as they are at 1200, and that doesn't work. So you've got to think of some approach to do it. And this is where the fun starts. So as I say, most LDMOS is designed for the wrong frequency. It's fine if you've got 2.3 gigs. This large aluminium slab is part of an amplifier that was designed for 900. There are some 2.3 gig versions of these that all you have to do is plug them in and change the bias around, and you get 300 watts on 13 SEMs, which I think Sam has got one. But if you want 1200 like me, you're in trouble. So you know, I keep pressing this to try and make the slides go. So we're okay for 13 SEMS, but if we want a 23 SEMS PA, we need to do a little bit of thinking, a little bit of what Mr. James Miller calls calculator on. So we're stuck. Now, we're not stuck. There's always some way of doing these things. If we had the technology to measure device impedances in situ when the things are powered up, that'd be great. You can get high power network analyzers where you can look at the actual device while it's operating and measure its impedances. If you can do that, life's a lot easier. But most amateurs haven't got an ordinary network analyzer, never mind one that can do it at high power. So you have to call upon something that I call the Bodger's subroutine. You've got to think things through. You think, how am I going to do this? If I can't measure it and I can't do anything else, I've got to do something. And this type of bodging approach is applicable to new designs, or it's applicable to retuning existing units. And very simply, this is for our software friends here, it's make an intelligent stab at what you think is going to work. Then, and you'll notice I've used Courier for this, like all the best computer jobs, Courier font. Then, cut, try, and optimize. Build it, tweak it, see if it works, find out which way it's going, and just keep on doing that until you end up with it's working satisfactorily. And that's end. So, I told you I was a bodger. A pair of cheap vernier calipers, because you have to measure things. This is all about finding out the initial thing is measure it. A roll of adhesive copper tape. Any RF engineer who's not got a roll of adhesive copper tape should leave now, because you have to have one. It's absolutely essential. A sharp scalpel. Those of you that didn't know ought to touch tools, probably a blunt scalpel, but a sharp one's better. A roll of plastic insulation tape. All will be revealed shortly. A Smith chart program. This is where you all go, oh, maths. A thing called AppCAD, which is another free program, which lets you look at microstrip dimensions and so on. So, because you do have to actually do some thinking. I may be joking about it being bodging, but you do have to think. And of course, you need something to bodge. Well, I'm handing round something to bodge. That's it. It's a lovely. It's a module made by Andrews, who are the antenna people with the red flash. And I looked at this and I thought, I want this to work. But I didn't quite get there, but as we'll see later, Chris did. So, I'm going to have to do a little bit of introduction to the Smith chart here to show you what I'm doing. Hands up anybody who's never seen a Smith chart. Good. I'm very pleased to hear that. Well, the first thing you know, have you ever seen a Smith chart like that with two sets of circles and colours? Well, that's known as an emittance chart, because not only can you plot impedances on it, you can plot admittances. Anybody know what an admittance is? Right. Very simple. Smash. If you've got an impedance, Z, the admittance of that impedance, which is called Y, is simply 1 over Z. So it's the reciprocal. It's really useful admittances because everybody knows if you take two impedances and put them in series like that, you get 2Z. Sorry about my writing. Yes? Ohm's bit of resistance. With admittances, if you've got two admittances and you put them in parallel, do you remember this formula? Where if you've got two resistors in parallel, it's 1 over R1 plus 1 over R2. Well, 1 over R is an admittance. So it's really easy. So 1 over the total impedance is 1 over Z1 plus 1 over Z2. Now, why am I waffling on about this? What that means is if you've got series circuits, you can simply add the impedances. If you've got parallel circuits, you use admittances because you can add them. Okay, that's enough about that. And the Smith chart, the two sets of circles are for plotting effectively, for plotting series and parallel things. impedances. So let's just bring up a. This is an interactive Smith chart, so I'm going to actually sit down and do this. This is a program that it's a free demo version of a program called Smith by Professor Deltzberger from Bern University. It's available on the web. So let me just give you a quick whistle-stop tour of a Smith chart. All these circles, first of all, the Smith chart is a way of plotting impedances, admittances, line lengths, and so on. The middle of the chart there, and if you look down at the bottom, where's my pointer gone? Let's have the green one. If you look down at the bottom, I've moved the cursor to the middle, and it's 50 plus J0. Don't be worried about the J. 50 is the resistive part of the series impedance, and the J is the reactive. That's the inductive or capacitive. Plus for inductive, minus for capacitive. So if you say 50 plus J3, it means 50 ohms and 3 ohms reactive. You all with me so far? So the centre of the chart, which is your line impedance, 50 plus J0 is 50 ohms. So you can plot any impedance. So if I plot an impedance there, right? So if I just select data point and plot from the keyboard, if I plot, let's say 30 ohms and 20 reactive, plus 20, that appears on the chart there. Okay? If I was to put minus 20 for the admittance part, it would be the corresponding position in the bottom. So top half is inductive, bottom half is capacitive, plus, minus. Easy so far. So, if you notice, if I now plot a point on one of these circles, let's plot a data point on, this time, on this circle here, that one there, right? That's okay. And if I plot another data point, and note what that number 2 is, it's, if I plot a second data point on that circle somewhere else, sorry I'm a bit slow, there, what you'll notice is those two values, that one is 27 ohms resistive, and that point is also, where's it gone? Okay. But so these circles are effectively circles of constant resistance. Okay. So anywhere along those circles, you get the same resistance on the red ones. That's because I plotted it on the green one. And on the green ones, you get a constant admittance. So they're just ways, it's just graph paper for impedance. Okay? But you can also put other circles on there. Because this is looking at a transmission line, you can put circles of constant VSWR. And you all know what VSWR is, yes? So they're concentric circles around the centre. So I'll come back to that in a second. Let me just go back to my presentation for a second. So it's just really a tool for helping you plot where the impedances are going. So to summarise, you've got circles of constant resistance, which are the red ones, constant admittance, which are the green ones, and constant VSWR are the circles in the centre. So you can represent any impedance, a complex impedance, which is resistors and capacitors, or resistors and inductors in series and parallel. You can plot them just by plotting them on that part, and you get a visual view of what the impedance is. Because don't forget, let me just go back right to where we started from. What we're talking about, what I'm going to do is I'm transforming impedances from the device impedance to 50 ohms. So I need to see where I'm going. So it gives you a good visual representation of where you're going. The charts use what you'll sometimes hear the term normalized impedance. That's simply the impedance itself divided by the characteristic impedance, in most cases 50. So if you see someone saying 1 plus J2, it's 50 ohms and 100 ohms reactive. So, positive reactances, inductances are in the upper part of the chart. Negative are in the lower part of the chart, so you can plot the impedance. Also, this is also a polar diagram in terms of wavelengths. And as you go round the chart, a complete circuit round the chart gives you half a wavelength. So not only can you plot impedances on this, you can plot the effects of long transmission lines as well. Right, that's probably enough about the Smith chart until we go back to doing a quick example. So, let's go back to bodging amplifiers. We've looked very quickly at the tools. What I'm going to hand around now is a bodged version of a similar thing. I've been looking at 900 meg cellular base station amplifiers and putting them on 23. The first thing to do, if you get some nice looking amplifier, look at the data sheets, look them up, and does it have the word internally matched? If it has the word internally matched, get your hacksaw out and use the aluminium for something more useful. Because generally you can't do much about it. Because by internally matching it, you've set the bandwidth that the amplifier can work over. So look for devices that are not internally matched. And we were very lucky in these amplifiers we got here that they're not. They're Motorola parts for 900 megs, but they're not internally matched. And generally, it's the high-power amplifiers. I had somebody phone me up and say, hey, I've got this 150-watt LDMOS device for 900 megs. Can I use it? And you look at the data sheets and internally matched. So avoid the very high-power ones. But the devices around about 40 or 50 watts tend not to be. So there's two ways you can do this. You can completely redesign the amplifier by stripping off all the matching circuitry, getting your copper foil out and sticking down new transmission lines. Yeah, so you can do that. Or you can try and use as much of the existing printed circuit board as you can and try and adjust the capacitor values to get a match. And it depends on the amplifier or how much of a rush you are. Because don't forget, you're talking about converting very low impedances to a 50 ohms. So generally, you look at the other thing you have to do if you're a bodger is look at everybody else's work as well. So get your French DB6NT power amplifier, whip the lids off, get your vernier calipers out and measure all the lines. So you can steal his ideas. I've said that in public as well. I'm only joking. But that just gives you an idea of what's involved in matching an amplifier. Because you'll find most of the designs around are very, very similar. There's only a certain way to actually match a device. So, creatively swipe. Why not? It's only amateur radio. So, you'll notice on this device, this is the device in the middle. You'll notice what I did here was a big wide piece of copper, and then a narrow one, and then back to a thin line. So you can actually step the impedance down in stages. Because the more stages you use, the wider the bandwidth you can make it. But for 23 sems, you can usually do things in a single stage. And that's what's called a T-step. You'll see it on all the data sheets and all the amp designs. They do like a T, first of all, to get the impedances down to 6, 7, 8 ohms, and then the step isn't as big. But generally, I've found, certainly with these Motorola devices, that a big fat line on the input of the right length will do it. And something similar on the output. But there's actually more to it than that. If you look at, now you understand Smith charts, you can see, this is an excerpt from the MRF 9045 data sheet. There are the impedances plotted, the input and the output impedances, plotted as lines. Series of points over, and you'll see, what did I say? 930 megs and 945. That's the only data you get. And you can see they're less than an ohm. They're positive J part, which means they're slightly inductive. And the output is about 2 ohms, and even lower impedance, it's nearly 0. So that's nearly resistive at that frequency. But you can see how they plot on the chart. So you can at least know roughly where you're starting at 900 megs. And what you can do is if you measure the capacitor values that the guys used in the 900 meg amp, and you measure the strip line dimensions, you can reverse engineer how he's come up to his design. So that gives you an idea that that's roughly the way to do it. But you have to do it at a different frequency. It turns out that when I actually did a design using this device and got it to match, I reverse engineered my own design back to the device impedances. And the device impedances have changed enormously, going from 900 megs down here to 23 sems. And if you look at the numbers, just look at the input impedance. The input impedance has gone from less than an ohm to 2 ohms. And the inductive part's gone hugely large. Yeah? So you can't just take the data sheets for 900 megs and hope it's going to work at 1296 with a new design. There are big changes, but there's a sort of a pattern. The impedances tend to go up and they tend to go more inductive when you get in high frequencies. So this is your start. This is the first stage of the Bodger subroutine. Make the assumption that the impedances are going to go up. And that's your starting point. And then you can bodge from around there. So what I did with these amplifiers was I reverse engineered the existing input circuit. I looked at what had been done at 900 megs. So the first thing you have to do, these things have microstrip lines. The microstrip lines widths depend on the type of material, the thickness of the board. So you have to measure those. So what you've got to do to work out what the material is you find a 50 ohm line, which is usually the one right on the output by the connectors. Find a 50 ohm line and measure its width. Once you've got its width, you can measure the board thickness with a pair of vernier calipers. Once you've got those two things, you can work backwards to get the board's material. And there's a very nice free application which lets you do that really easy, and that's called AppCAD. AppCAD's got a nice microstrip thing that lets you calculate impedances. So let's say we've measured the width of the board, and it comes out at 1.8 millimeters. We've measured the height of the board as 0.8, and we've guessed that it's 1 ounce copper, which is 0.0355 millimeters. So you can stick these numbers in there. We're not bothered about the length. You can press the calculate button, and down here you've got the dielectric number, which is the board material. Press the calculate button, and you find it's 80 ohms. So that's clearly, it doesn't have a dielectric constant of 1, but you wouldn't expect that because that's air. So what you do is you plug here all the common values for board materials. So let's try, and you can find these on data sheets, Rogers and people like that. So we'll first... Yes, they're actually in AppCAD. So what we can do is we can select, I don't know, let's select one of the materials it gives you. Let's try 2.33, which is a common one. And we're at a gigahertz roughly. And you just do calculate, and it's 58 ohms. So we're still not quite 50 ohms. So let's try a higher value. Let's stick in 3.5, only because I know the answer, and it gets to it quicker if I do that. If you plug in 3.5 into this, which is one of the standard materials, let me just get to the custom value. Just bear with me. So if I just put 3.5 in there, and do calculate. Oh, I put 3.5. And calculate. That's going to give you roughly 50 ohms. So you have a reasonable assumption now that this is built on a board with a dielectric constant of 3.5. So you now can look at the printed lines on your board, and you can say, well, I know what length it is. I know what frequency I want it to work at. I know what width it is, so I can work out that line's impedance and its length. So I now have a number I can use. So this is all the sort of reverse engineering stuff. So we can do that. You can measure the L's and the C's and the microstrip lines. It does involve taking them off the board, but with chip capacitors it's not that difficult. But you can measure the C's. You can get a reasonable idea of the capacitance of a chip capacitor with one of David's with one of David's boxes that I think you've got a sort of an LCR bridge, haven't you, available? Yeah. So you can measure the capacitors, you can measure the inductances. So what you end up with is a good idea of the guy's circuit. But what you must remember, of course, is when you're going from 900 to 1296, the lines in wavelengths will actually be longer at 1296 in wavelengths. But it's just a straightforward ratio of 900 to 1296. So you can work out the line lengths in wavelengths, their impedances, you work out all the capacitor values, and then you just simply have to do a bit more reverse engineering. And I just made the assumption that on all devices the impedance is going to increase. So you just guess the impedance and stick it on the Smith chart and see what sort of match you might get. And then you go into this iterative process of tweaking. Okay? Or you can start changing the capacitances. Look at the input match. Start off with the input circuit, put your VSWR meter in, measure the input, and see if changing the capacitor value makes the match better or worse. And it takes time, but you can do it. So let's just do a little example. Let me just... Somebody's very kindly swept up my piece of paper that had my example. No, here it is. Let's just say we had an example where we found that we had a matching circuit. Let's say the matching circuit looked like this. I hope you can all see this. There's the FET. We found we had a strip line, a shunt capacitor, and a series capacitor at 900 megs. And we measured the length, and we measured this as 10 picofarads, and we measured that as 10 picofarads, and we measured the length of that as 0.131 of a wavelength. If you convert that to the equivalent wavelength at 23 sems, you end up with 0.188 lambda. Okay? It makes it longer by 1296 900ths. Okay? So, we're going to make a few assumptions here. Let's go back to my show again. So, and let's say that we looked at the data sheet of our device and it said it's 1.7 plus J1 at 900 megs. And we found it matched with a 0.131 lambda line. You didn't tell me. And it worked out to be a 12 ohm line, characteristic impedance, and a 10 puff shunt and a 10 puff series. Now, and let's just make that leap of faith that I made, and let's just assume that the impedance changes to 3 plus J3 as a first guess, because this is your first stab before you try it. So let's plot, instead of plotting 1.7, we'll plot 3 plus J3. Okay, so let's go back to the Smith chart program. But first of all, let's start off with the original design so that you can see what's happening. The first thing that we do is we plot the impedance of the device at 900 megahertz, and we say it's 1.7, and it's, what was it, J1. Okay? So that impedance is down there. Can you see the red square? Right? We've then got a series transmission line now, and you see the circuit building up in the top corner there. We've got a series line with 12 ohms impedance, okay, and at 900 megs it's 0.131 lambda long. And can you see as I move around this point, I get to about 0.131, right? So that's now transformed the impedance to 4.3 plus J 14.6. Okay. We then have a shunt capacitor, and that's getting us fairly close to the middle. Can you see we're coming towards this 50 ohm point here? So if we have a 10 puff capacitor there in shunt and a 10 puff series, lo and behold, you end up in the middle. So that matching network has given you a match from the transistor impedance to 50 ohms. So you've checked the guy's original design and it seems to make sense. So let's make our leap of faith and say let's assume the impedance has moved up here somewhere to 3.3. So I'll get rid of this. So I'll plot my guessed impedance as 3 and 3 inductive, which stacks up with what I discovered with the devices. So you see that's moved out to there now. This time, the other thing, we now have a series line again, but this time hang on, sorry, I've missed something. I forgot to change the frequency. Hang on, let me just get rid of that for a second. It's probably doing it on the fly. Let me just get rid of that. I thought you might have spotted that. So 3 plus J3, 3, and this time we're at 1296. Okay. There. Right. So we've got a series line, but now remember this is now no longer 0.131 wavelengths long because the frequency has gone up. It's longer. So we now put the same width line because we've not changed the PCB. And we now go 0.188, which takes us round to there. Yeah. You can probably actually see that if I carried on with that line and made it longer, we'd end up with a match. So in fact, what I could do with this was simply just take all the capacitors off, extend the length of the line if there's room on the board with our copper tape and our scalpel, and you'd actually end up with a matched amplifier. But what I'm going to do is I'm going to keep the same line length, which is now 0.188, roughly, right? And find out what shunt capacitance I need. So I put a shunt capacitor in there, and I need 1.2 picofarads. So I've lowered the capacitance needed to match this, and we've got a match. So you can see what I'm doing. So what you do now is you think, well, I've made a guess at the impedance, and I've said, let's just guess. Now we'll build it. We'll change the capacitor from a 10 puff to a 1.2 puff and see if it matches. See which way the match goes. Or we simply take the capacitor off, put a trimmer on it, and adjust it till it matches. And 9 times out of 10, you'll get it to work. So can you see what I mean about this process of make a guess, build it, see if it works, and I've done that quite successfully with these amps. It takes a while, but you can see how you can use the Smith chart tools, and you can use the AppCAD tools to get you to the starting points. So I think that's probably enough. Are you all following me so far? Yeah, everybody's happy. Okay, let's just run back to there. Now it might be that the impedance is not changed to 3 plus J3, but you will be able to, by measuring your VSWR, you'll be able to see which way it's gone. If it's got worse, you must have done something wrong, so you have another stab. If it's got better, great, you're getting there. And the nice thing about these devices is you can leave the output match as it is and not get any power. And you can sort out the input matching first, and you're pretty close. And then you can use the same procedure on the output, but this time instead of going for VSWR, you go for best output power and minimum current. So guess, tweak it, validate it, measure it, and go around the loop. And you very quickly find whether you're not going to be able to do it. This is generally when you find out that the device is internally matched. So that's the sort of process I've been using. This is why I call it the Bodger's approach. It's not professional, but it does work. You know, I have done this with a few. There's a few do's and don'ts generally about LDMOS amplifiers. Try and avoid shunt capacitors. Because you've got very low impedances and quite high power, you've got lots of current. You can typically get 1.5 or 2 amps flowing in a capacitor in these things. And it's quite entertaining. I said earlier on about using trimmers before you put the capacitors in. You can melt them if you try and do it in the output. So try and avoid shunt capacitors. And I think you saw earlier on with that design before, you can sometimes do away with capacitors altogether. You saw earlier on I did that where it moved around the Smith chart with no capacitor. So if you can do that, even better. watch the output capacitors rating. You can typically get 100 watts into 50 ohms is 1.4 amps. That's a lot of RF, that. Do try and avoid trimmers apart from the early bodging stage, because you can get away with it for a few seconds with a trimmer, but they very rapidly heat up, change value, and then explode. So shunt and series capacitors can have high, so you've got to use decent capacitors. Try and recycle as much of the amplifier as you can, because generally these things have got very expensive porcelain capacitors and lovely stuff like that, nice strip lines. So try and use as much of the original board. Try simply do the whole thing just by changing capacitor values. But I didn't have the patience, and I simply ripped most of the design off and rematched it. Don't bother trying to use internal matching devices. Somebody might have done it, but I've never had such success. Yes.
I'll make a comment on that.
Right, okay, yeah. The only thing that destroys LDMOS devices is too much gate voltage. You'll notice most designs have got a reasonably high value resistor in series with the gate bias. If you don't put that in, you just get the bias wrong, it goes bang. And that's it. Fine if you've got the devices but not at £30 a piece. And don't use FR4 for anything more than power. My little amplifier that's going in Radcom fairly soon, hopefully. Please, all the reviewers who are here, it's very good. I tried to build this on this is a single-stage LDMOS device, which I don't look at the PCB. It's an awful bad PCB. But I built that on FR4 first, and I got 30 watts out of it. And I thought, oh, this is good. And I did it, and I was just about to give it to Colin G8LBS, who was my beta tester, but I thought I'd better put it on for a while. So I switched it on, left it running 30 watts, went downstairs and made a cup of tea, and I came back upstairs and took the lid off the box, and it was full of white smoke. And what had happened was the dielectric losses were so high in FR4 that the thing had actually heated up so much, it had burnt the board. So I went over to RF35 from Taconic, and I've had that running for an hour at 40 watts, and it just gets warm. Oh, by the way, when you test the temperature of your PAs, turn the RF off first, because if you put your finger on an output line with 40 watts in it, it gets very hot. And RF burns go deep. Believe me, I've done it. So just a few tips. I think that's the end of the presentation. Yeah, just a couple of acknowledgements. The pictures came from an ST website, and Smith you can get just Google Smith and University of Bern and you'll find it. There's a full version which will cost you $100, but the free version lets you do, I think it's 5 stages, but you can't save. But it's a really nice, easy program to use. There are alternatives. There's a thing called QuickSmith, which Sam gave me a copy of recently, which I've not tried. But there's lots of Smith charts. When I was a lad and I designed RF professionally, we used to have to draw them out on paper with a pencil, but there are programs around. And finally, AppCAD is downloadable. Once again, if you just Google AppCAD, it's a former HP program, but it's some other website hosting it now, and it's fantastic. It doesn't only do this, it does amplifier design, system design. I think Sam's referred to it in his column before. So that's it. How to be